I will speak about operator estimates for homogenization of the Levy type operators with periodic coefficients. The results are quite recent, obtained this year, and this is joint work with Andrei Pyatnitsky, Vladimir Slouch, and Elena Zhizhina. Let us introduce our main object. It is a non-local operator, A epsilon. It acts in L2RD. It depends on the small parameter epsilon. This is a formal expression, not the definition, just formal expression for the operator A epsilon. It depends on the parameter alpha. Alpha is here, and alpha is a positive number less than 2. And here we have the coefficient mu depending on two variables. We assume that mu is bounded, positive definite. It takes values between mu minus and mu plus. It is periodic in both variables with respect to the lattice ZD. And it is symmetric. Mu of xy is equal to mu of y and x. The precise definition of this operator is given in terms of the quadratic form. So we consider this quadratic form. It is non-negative and closed. It is defined on the Sobolev space H of order alpha over 2. And so this quadratic form generates a self-adjoint operator in L2, which is our operator A epsilon by definition. And the coefficients oscillate rapidly for small epsilon, the coefficient mu. And we are interested in the behavior of the resolvent for small epsilon. What was known before? In 2019, Kasman, Pyatnitsky, and Zhizhina proved that the resolvent of A epsilon strongly converges to the resolvent of A naught as epsilon tends to 0. This A naught is the so-called effective operator. It is of the same form as A epsilon, but it has a constant coefficient, mu naught. Mu naught is just the mean value of mu. Omega is the cell of the lattice, the unit cube. Note that we can write the effective operator as follows. It's minus Laplacian to the power alpha over 2 multiplied by mu naught and the constant C naught, which is written here. C naught depends on D and alpha. The domain of A naught is the Sobolev space H alpha. We prove that the resolvent of A epsilon converges to the resolvent of A naught in the operator norm. This is our first result. And we obtain error estimate 3. You see that the error depends on alpha. For alpha less than 1, we have order epsilon to alpha. For alpha greater than 1, less than 2, epsilon to the power 2 minus alpha. And the order deteriorates if epsilon is close to 2. Yeah? And for alpha equal 1, we have epsilon and this log term. The constant C is well controlled. It depends on dimension D, on alpha, mu minus, and mu plus. This is our first result. We will see that this order epsilon to the power alpha is optimal. So for alpha less than 1, already the principal term of approximation gives the optimal, is optimal. But this is not so for alpha greater than 1. And we improve approximation taking into account characters. This is our second result, theorem 2. Here alpha is always greater than 1. Let k be a natural number, and alpha is greater than 2 minus 1 over k and less than 2. Then we prove approximation 4. This is the principal term, the resolvent of A naught, and the first k characters are taken into account. Then we have the error epsilon. If epsilon is greater than 2 minus 1 over k and less or equal than 2 minus 1 over k plus 1. And in this interval, when alpha is greater than this number, less than 2, we have order epsilon to the power k plus 1 times 2 minus alpha. Recall that without characters, the error was epsilon to the power 2 minus alpha. Now it's better. The characters km are given by this expression. They are pseudo-differential operators of negative order. Km involves the resolvent of A naught to the power m plus 1. And it is multiplied by the differential operator, divergence type operator, diff g gradient to the power m. This matrix G is a symmetric matrix, is constant symmetric matrix, and it is defined in terms of the solutions of some auxiliary problems. This is usual in homogenization theory, that the effective coefficients are defined in terms of the solutions of the so-called cell problems. Now we will define this matrix G on the next slide. First, we introduce such notation. So omega is the cell of the lattice, and HS tilde of omega is the subspace in the Sobolev space HS omega, consisting of functions whose periodic extension belongs to HS log. So this is periodic subspace. Next, we introduce the solutions Vj of the auxiliary problems. Vj belongs to the class H tilde alpha over 2. It has 0 mean value, and it satisfies this identity for any test function phi in the same class. You see that here one integral is over omega, and the second integral is over RD. And we assume that the functions Vj and phi are extended periodically to RD. It's easy to show that the solution exists and it is unique. Next, we define the coefficient mu star of z by this relation. Note that this mu star is periodic and it has 0 mean value. And now we define the matrix G. So G is a symmetric matrix with the entries G, L, J. Here we have the sum of two terms. In the first term, this mu star, and in the second term, we have these solutions Vj and Vl. And now this matrix G is defined, and recall that the characters Km are given by this expression. Now let us discuss the method. We rely on the operator theoretic approach. It was suggested and developed in our joint papers with Mikhail Birman, and we applied this approach to study homogenization of second-order elliptic differential operators with periodic rapidly oscillating coefficients. This approach is based on the scaling transformation, the Flaquet-Bloch theory. It's the direct integral decomposition for periodic operators. And the main part, calculation of approximation for the resolvent in terms of the spectral characteristics of the operator at the bottom of the spectrum. So the main idea of this approach is that homogenization can be studied as a spectral threshold effect at the bottom of the spectrum. For differential operators, we apply the methods of the analytic perturbation theory on this third step. But now, for non-local operators, these methods are not applicable. So we have modified this operator theoretic approach. Let's go in details. By A, we denote our operator when epsilon is 1. So this is operator with the coefficient mu of x, y, no epsilon. Consider the unitary scaling transformation, P epsilon, defined by this relation. It's unitary operator in L2. Obviously, by this scaling transformation, A epsilon transforms to this operator, A with the coefficient epsilon to minus alpha. We have this relation. We have a similar relation for the effective operator. And then we deduce this identity. To prove theorem 1, we have to estimate this norm for this difference of the resolvents. This norm is equal to that norm. Yes. Here we have the resolvent of A, which does not depend on epsilon, but it is taken in a regular point minus epsilon to alpha. So the regular point now depends on epsilon. And we have extra factor, epsilon to alpha. This is the first reduction. So in order to estimate the left-hand side, we will estimate this norm. And we remember that we have extra epsilon to alpha. So the required estimate 3, this is estimate from theorem 1, I repeated it, is equivalent to estimate 5 for this difference of the resolvents. We will prove estimate 5. The bottom of the spectrum of the operator A is point 0. And it is natural that for small epsilon, we take resolvent in point minus epsilon to alpha, which is close to the bottom of the spectrum. It is natural that for small epsilon, we can approximate the resolvent in terms of the spectral characteristics at the bottom of the spectrum. Spectrum of A. Indeed, let us consider a small interval, 0 delta, and by E delta, we denote the spectral projection of our operator A corresponding to this small interval. If we multiply this resolvent by the orthogonal projection, this operator is uniformly bounded And this term can be attributed to error. So we have reduced the problem to approximation of the resolvent multiplied by the projection E delta. Then it follows that the optimal accuracy is O of epsilon to alpha. And in theorem 1 provides optimal accuracy for alpha less than 1. And for alpha greater than 1, we have theorem 2, approximation with characters. Now the second reduction is the direct integral decomposition. Our operator A is periodic. And then it admits the direct integral decomposition with the help of the unitary Gelfand transform. The operator A is unitarily equivalent to the direct integral of the operators A of psi. The parameter psi is called the quasi-momentum, and it belongs to omega tilde, this cube, minus pi to the power d. It's the cell of the dual lattice. A of psi is a self-adjoint operator in L2 omega on the cell. It is also defined in terms of the quadratic form. The quadratic form is written here. This quadratic form depends on psi and is defined on periodic functions, the Sobolev space H tilde alpha over 2. This form is non-negative and closed, and it generates a self-adjoint operator, A of psi. The effective operator A naught also admits the direct integral expansion. The operators A naught of psi are similar to A of psi, but they have constant coefficient mu naught. And so A naught of psi can be written as follows. Using the direct integral decompositions, we see that the required estimate 5, I repeat it here, is equivalent to estimate 8. This is the same estimate of the same order, but now for operators depending on quasi-momentum psi. And here the operator norm is in L2 omega. We have to prove this estimate for all psi. It must be uniform with the same constant C for all psi in omega tilde. This is the second reduction. And now we study this operator family, A of psi, and we are interested in the spectral properties. The operator A of psi acts on bounded domain, and the spectrum is discrete. Denote the consecutive eigenvalues by lambda j of psi. Using simple variational arguments, it's easy to check that the first eigenvalue is of order modulus of psi to alpha. It satisfies such estimates. And the second eigenvalue is separated from 0 by this constant. It follows that if psi is 0, it will be our unperturbed operator, A of 0. The bottom of the spectrum is lambda 1 of 0, and it is point 0. The kernel is one-dimensional. It consists of constants. Then, for sufficiently small psi, the modulus of psi less or equal than delta naught is this number, the spectrum of A of psi on the interval from 0 to d naught over 3 consists of just one eigenvalue, lambda 1 of psi. This is the spectrum of unperturbed operator A of 0. We have eigenvalue lambda 1 of 0 equal to 0, and here lambda 2, and so on. And this is the spectrum of the perturbed operator A of psi for sufficiently small psi. So on the interval from 0 to d naught over 3, just one eigenvalue, lambda 1 of psi. And the second is greater than d naught. And it turns out that for our problem, only this first eigenvalue is important, and of course the corresponding eigenfunction. Okay. Conclusions. It suffices to approximate the resolvent only for small psi, modulus of psi less or equal than delta naught, because otherwise the operator A of psi is positive definite, and the resolvent is uniformly bounded. We attribute it to error. Denote by f of psi the spectral projection of operator A of psi corresponding to the first eigenvalue for the interval 0 d naught over 3. If we multiply this resolvent by the orthogonal projection, again, this norm is uniformly bounded and it goes to error. So we reduce the problem to approximation of the resolvent of A of psi multiplied by f of psi for sufficiently small psi. And the main technical work is to find approximations for this spectral projection f of psi and for the operator A of psi multiplied by this spectral projection, the so-called threshold approximations. Lemma 1. Denote by P the orthogonal projection of L2 omega onto constants. This is the kernel of A of 0 of unperturbed operator. Then for small psi, we have the following estimate. We approximate projection f of psi by projection P. The error is of order theta of psi, which is written here. And you see that the order depends on alpha. Lemma 2. We approximate the operator A of psi times f of psi by the projection P multiplied by some constants, C naught, mu naught, and modulus of psi to alpha. Here the error is of order theta squared. Now it's easy to complete the proof of theorem 1 to find approximation for the resolvent. So we have reduced the problem to approximation of this operator, the resolvent of A of psi multiplied by spectral projection f of psi. We consider this difference sigma. And we have the following identity. It's in fact like resolvent identity, but with projections. Yeah. The first two terms contain the difference f of psi minus p. But for this difference, we have lemma 1. The third term contains this difference. Yeah? For this difference, we have lemma 2. And using lemmas 1 and 2 and the obvious estimates for the resolvents, we immediately obtain such estimate for sigma. Here we have two parameters, psi and epsilon. And it's easy to deduce the second estimate for sigma, where we have only epsilon. And using the reductions described above, we obtain the required estimate. We recall that we have reductions, direct integral decomposition, and scaling transformation, and in fact, this completes the proof of theorem 1. Theorem 2 is proved similarly. Of course, the proof is much more complicated, but the ideas are the same. We obtain, to prove theorem 2, we obtain more accurate threshold approximations for the spectral projection f of psi and for this product a of psi times f of psi. Thank you very much.